All right, so a question has come up about why I use for a square root a 1/2. And what we want to look at is some things that'll happen. I'll have a tendency that when it is an irrational number, I'll use square root of 2 because that's a number. But when using with variables, I'll use the rational exponents. And what we want to look at is, let's look at what happens when I have the square root of x times the square root of x. Our square root law says, hey, if I have two square roots together, that's going to equal x. Right? You multiply the same thing with a square root, it nullifies the square root. So we could think about this as if this was some unknown base times some unknown base. It's going to equal x to the first. It's saying the same thing. I have two things, some base to unknown exponent, some base to unknown exponent. I have x to the first. Now I just want to convert my square roots to some type of exponent. So my exponent rule says I add these, and my law of equality will say that the exponent is 1/2. And so I can write x to the 1/2 in place of a square root. Well, look what this does for us. It says x to the 1/2 times x to the 1/2. Well, our rule says that's the same as adding our exponents, or x to the first. So we get all of the utility of a square root with the same rule set as exponents. This means that we could have x to the third times x to the 1/2, which equals x to the 3/2. And so we can have the concept of taking something to the third power and taking the square root. That comes out as being the same as this. Since this functionally works with addition, with the exponent rules, and roots are the inverse of powers, this works out nicely. So if I have my power rule, x squared, and I take it to the 1/2 power, that's equal to x, because my power rule says I multiply these. That's the same as writing x, the square root of x squared. And so rational exponents save us from A, this odd symbol, and B, memorizing a different set of rules. The only thing is, if the denominator is even, then for real answers to come out of here, x has to be greater than or equal to 0. And that's the only restriction we get. But we get a similar thing when we make division out of multiplication. Right? A times B equals C, and then if we reverse that, C divided by B equals A, but B can't be 0. Every time we create one of these little weird inverse rules, we'll get a little bit of an extra restriction. And so that's where our rational exponents come from.